sections 23.4 and 5, the mixed aldol reaction. So I have an aldol depicted for us here, and what I want you to see is that this could come very readily from two different aldehydes. First, the one outlined in the blue dash there, and then this all portion would have come from a separate aldehyde. Of course, this aldehyde would have been acetaldehyde, and the other is propionaldehyde. And here in the middle, I'll put a X on it, is the bond that we made in the aldol condensation. So looking at the aldol backwards, then we could readily imagine that we could take this apart at that bond and have propionaldehyde and acetaldehyde as our two components. So now let's think about what would happen if we mix these two together. If we put them together with, say, sodium ethoxide, what would we get? Well, we could make the enolate here and it could condense the way that we want. Well, let me switch the colors there. We'll put in the bond that we're making here with. So there are two components, but is that the only one we're going to get? Well, relatively speaking, we would expect the acidity to not be very different between those two. And of course, how would the enolate, once it's formed, know that we only wanted it to react with acetaldehyde and not with another molecule of the starting material? So we could also get the enolate that comes from addition. And I'll make the new bond in white. But the aldol product from self-condensation. In addition, we could have formed the enolate from acetaldehyde and condensed it with propionaldehyde, and it could have also undergone self-condensation. And so we have four different aldol products, and of course we know now from the earlier sections these can eliminate. In fact, that's the driving force for this reaction, and produce the alkenes at each of those positions, and those would have cis and trans. So this is a complicated problem. But it turns out there is actually a solution for it. That solution is the mixed aldol, where we use a couple of different things. First, we want an unenolizable component, and that would be something like benzaldehyde. Or second option here is we use a very acidic component, carbonyl. That would be something like a beta dicarbonyl complex. So let's look at these two solutions. If we take this enolizable carbonyl. We react it with benzaldehyde. Sodium methoxide. And we go ahead and heat it up a little bit. Turns out we can actually get a very good yield. And the product goes to one side because we can't do the elimination on the other. Remember, this is all reversible. So here we have the example of number 1, where we have an unenolizable carbonyl compound. Benzaldehyde has no enolizable hydrogens. Let me draw it out for you here to illustrate the point. All right, where's the alpha carbon? There's the alpha carbon. But of course, what's there? There are no hydrogens, right? 4 bonds, but no hydrogens. So that's not enolizable. Now, the alternative here, number 2, is to use something very acidic, so we can do that. We combine this with something that actually can be enolizable. Okay. Then again, treat this with a little bit of heat and sodium ethoxide, because you get preferential deprotonation here. It's going to take a bit. This won't be catalytic in base. We can drive that reaction to completion also.